Hello everyone, welcome to the lecture series on analog electronics. This lecture series is a part of Let's Crack the Gate initiative by TEQIP Faculties. Today we will discuss a topic called transistors, limits of operation and operating point, which also includes the DC load line. So far we have seen how a transistor operates, what are the different characteristics of a transistor in different configurations, right? We also saw that a transistor can be used as a switch as well as an amplifier. Our area of concern in this course is to consider the transistor as an amplifier. Okay. In order for a BJT to be operated as an amplifier, it should be working in the active region. So we have to fix the operation of a BJT inside the active region so that it operates as an amplifier. Okay. Also, there are some limits on the operation of the transistor in this region. That is, we know that whatever electronic equipment we have, it will have a maximum current limit, maximum voltage limit. Similar way, this transistor also has a maximum limits. So let's look at the output characteristics of a common emitter amplifier configuration. So here we have VCE, collector to emitter voltage, and IC, which is the collector current. So this is the output current and output voltage. So we have seen this characteristic. So this is how the characteristic looks like, right? Now we know that any electronic component will have a maximum limit on the current. So IC has a maximum limit, and that maximum limit is called IC max, maximum collector current. Similar way, there is a maximum voltage we can apply across this transistor. It is called VCE max. Now we also know that there is a VC sat here, which corresponds to the saturation voltage, and below VC sat the transistor is in saturation, and above VC sat the transistor is in active region. So in order for the transistor to be in active region, our voltage must be above VC sat. Okay. The reason is below VC sat the current voltage relation is not linear, and after VC sat, that is in the active region, the current voltage relationship is linear. If the current voltage relationship is linear, then only we will get a distortionless signal at the output of an amplifier. So there is VC sat, which is the minimum voltage to be applied to a transistor. Then we know that this is the cutoff region, and this is for IB is equal to 0, right? When IB is equal to 0, there is a collector current in the transistor, and that collector current is called ICEO, right? We have seen that. So when IB is equal to 0 microampere, there is a collector current, that is ICEO. So the minimum collector current for the transistor to be operated in active region is ICEO. So if we keep that in mind, there is a minimum voltage and minimum current corresponding to this point. There is a maximum current corresponding to this point, and a maximum voltage corresponding to this point. So we can show this in the figure. So this is the maximum current limit. This is the maximum voltage limit. This is the minimum current limit. And this is the minimum voltage limit. VCE SAT. Now there is also a power consideration, that is, there is a maximum power that can be dissipated in the transistor. If we go beyond that level, the temperature limit of the transistor will be exceeded. So there is another limit to the operation of a transistor, and that is the power limit. So we can show the power limit on the graph as this. So there will be a voltage corresponding to the maximum current, which gives the maximum power, and there will be a current corresponding to the maximum voltage that gives a maximum current. So this is the curve that denotes the maximum power dissipation criteria. The region of operation is inside these limits. Here, here, and here. The transistor can be operated in this region, which is also the active region limited by the power and voltage constraints. So this is the limits of operation, and this is the operating range of a transistor. Now if we write this limits of operation, we can write the limits of current as ICEO is the minimum current through the collector, IC must be greater than that, and it should be less than IC max. Now VCE SAT less than or equal to VCE less than or equal to VCE max. This corresponds to the voltage condition, and the power condition is VCE into IC must be less than or equal to the dissipated power, the maximum dissipated power PC max. So these are the limits of operation of a transistor. Okay. So in a transistor data sheet, all these parameters will be given. That is, IC max will be given, VCE max will be given, VCE SAT will be given, PC max will also be given. ICEO is not usually given. Mostly ICO is given. We can find out ICEO from ICO. Okay. Now we will see the next topic, that is DC load line and operating point. So when we look at operating point, the operating point is the value of voltage and current that corresponds to the distortionless linear output for an amplifier. Okay. So far we have seen that our BJT was supplied with DC signals, our BJT was supplied with DC voltages, and when we change the DC voltages, we get different DC currents, right? But an amplifier will have both DC components and AC signals at the output, that is DC components and AC components at the output. So when we design or analyze an amplifier, we have to consider these two, that is DC components and AC components at the output. The DC components that we select, that is the DC supplies as well as the resistors we select, are used to select an operating point for amplification. Okay. So we know that for amplification our transistor must operate in the active region, and that must be ensured through proper selection of DC voltages and currents. So this proper selection of DC voltages and currents, or the proper selection of operating point, is called biasing. So it is the proper selection of operating point, which is also called Q point or quiescent point. So this process is called biasing, that we will discuss in the next lecture, but we will see why this biasing is a necessity, why this selection of operating point is a necessity. So in order to analyze this biasing as well as operating point problems, we will assume that the value of VBE will be equal to 0.7 volts, IE is equal to beta plus 1 IB, and as the third point, IC equal to beta IB. So with these relations, we can start the analysis of different biasing circuits of a BJT. Now this is the characteristics of the BJT. The different limits of operation are also shown here. This is IC max, VCE max, this point is VCE sat, and this point is ICEO, and this curve corresponds to the maximum power dissipation allowed. So this is corresponding to PC max. Okay. Now I have also identified some operating points in this diagram. There is A, which is here, there is B, which is here, now there is C, which is here, D here, and E here. Now we have to identify which operating point is the most suitable for amplification operation. Okay. So let's say A is our quiescent point or our operating point. The problem with A is, now the current and voltages are 0. First thing is, the transistor will not be in the active region, and second thing is, now we are going to apply our AC signal to this amplifier, which is operating at this point because of the DC supplies. So if we apply AC signals here, there will be the positive half cycle of AC signal will be completely amplified, but the negative half cycle falls below this line, right, below this IC equal to 0 line. So below this line, the signal will be completely cut off from the output. So A cannot be an operating point. The same problem is there with B. In B, which is very close to the cutoff region, because of this, some or most part of our negative half cycle will not be present at the output. So B is also not a suitable operating point, so as A. Now if we look at C, the problem with C is it is in the saturation region, and because it is in the saturation region, it is non-linear. So the input and output relation will be non-linear. Also, for negative values of voltage across collector to emitter, there will be a cut in the output. So C is not a suitable operating point for amplification. If you look at E, it is beyond the maximum power limit of this transistor. So that is reason enough for not choosing E as an operating point. So if you look at D, the point D is inside the active region. It is not close to the zero current line or close to the VCE sat line. So this point is the most suitable operating point in this case. Out of these 5 cases, point D is the most suitable operating point or Q point. Okay, so when we select a transistor for amplification, we should make sure that the operating point is well within the active region, and any change in input signal will not put it out of the active region or out of the limits of the operation of that particular transistor. Okay. Now the next topic is called DC load line. So this is our characteristics. So now our operating point is at D. In order to choose D as the operating point, that is when there is no signal, this should be the current and voltage, that is the current corresponding to D and the voltage corresponding to D must be the current and voltage supplied by the DC supplies, right? So for the DC sources to apply this much current and this much voltage, there will be a resistive network applied across it, across the transistor. Okay, so that resistive network and transistor will have a characteristics. Since it is a resistive network, it will be a straight line, right? So that characteristics will look like this, and the characteristics of this external network connected on the transistor, that is called the DC load line. The DC load line can be drawn by assuming two things. The first thing is, we will assume Vc equal to 0. When Vc equal to 0, we will get an IC corresponding to that, which is this point. This corresponds to Vc equal to 0. Then we will assume that IC is equal to 0. That corresponds to a VCE, that is this point. So by assuming these two conditions, we will get a straight line. And this straight line is a property of the external network connected to our transistor. And we need to make sure that the external resistances and the sources will make the transistor work at the Q point we have chosen. Okay. So this is the concept of DC line, which we will explore extensively in the biasing part of our course, the DC biasing of transistors. Okay. Now we will discuss some problems. The theory of those problems we have already discussed in the previous lecture, and in this lecture we have to solve some problems related to the region of operation of a transistor. How to find the region of operation of a transistor. Okay. So this is our first problem. That is, in the circuit shown below, the silicon transistor has beta equal to 100 and negligible reverse saturation current. Calculate IB, IC, IE, VCE and VCB. Okay. So when you look at this, you can see that this is an NPN transistor. So this base emitter junction, the base is connected to a positive supply and emitter is connected to the ground. That means this is going to be forward biased. Base emitter junction is going to be forward biased. The transistor is not in cutoff region. So we can write that BJT not in cutoff region. Next, we have to find out the region of operation of BJT so that we can find out the values of IB, IC, IE, VCE and VCB. So for that, we will assume that the transistor is in active region. This was our first method, right? If transistor is in active region, we know that VBE is going to be 0.7 volt because this is a silicon transistor. So we can apply KVL in this loop. There will be a current flowing here, which will be IB. Here the voltage VB is 0.7 volt. This is base and this is emitter and this is collector. VB is 0.7 means we can find out IB. What will be IB? IB is given by the current here. IB is the current here, right? So IB will be given by 5 minus 0.7, because if you look at VBE, E is connected to ground. So VBE and VB will be the same, right? Look at the figure. VE is equal to 0 because it is connected to the ground, and VBE we know as VB minus VE. So if VE is 0, VB and VBE will be the same, right? So VB, so IB is actually, let me write the equation. This is now actually 5 minus VB divided by the resistance 200 kilo ohm. Now the value will be 5 minus 0.7 divided by 200k, and this value of IB will be 21.5 microampere. Okay, clear? Okay. Now we know IB. After finding IB, we can find out the value of, IC, right? Now IC will be equal to beta IB plus beta plus 1 ICO, but here in the question it is given that there is a negligible reverse saturation current, so we don't have to consider ICO. So IC is equal to beta IB, beta is 100 and IB is 21.5 microampere. That means IC will be 2.15 milliampere, right? Now after finding out IC, we can find out VCE. Now VCE is given by, VCE is equal to this voltage minus the drop in this resistance, right? So 10 minus the current IC, which is 2.15 milliampere, into the resistance, which is 3 kilo ohm, 3 into 10 to the power 3. Now the value of VCE will be 3.55 volts, and we know that VCE sat for a silicon transistor is 0.8 volt. So when we compare this, we get that VCE is greater than VCE sat. That means our assumption was right, that is, the transistor is actually in active region. So our equations all hold. So we have already got IC, IB, VCE is already there. Now we need to find IE and VCB. We know that IE is equal to IC plus IB. So this will be 2.17 milliampere. And the last thing is VCB. VCB can be written as VC minus VB. Now we know that VB is same as VB, which is 0.8. What will be the value of VC? We have got VCE, right? Since VE is 0, what will be VCE? VCE will be same as VC. So VC and VCE are same. So VCB will be VC minus VB, which is 3.55 minus 0.7 volts, and that is given by 2.85 volts. So these are all the answers we need. Okay, now let's do the next problem. So the next problem is the same one only, but here we just need to find the region of operation of the transistor. We have already found it, but in this case we will use the second method. So here assume that the transistor is in saturation region. Okay, in this case we know that VBE sat will be equal to 0.8 and VCE sat will be equal to 0.2 volt. Okay, okay, now we can find out the value of IB. IB is given by 5 minus VB is sat, because that is the voltage across these 2 points, and emitter voltage is now 0. 5 minus 0.8 divided by the resistance, which is 200 K. Now this will give you IB. And what is the value of IB? This will be 21 microampere. Then we need to find the value of IC sat. IC sat is 10 minus VCE divided by the resistance, is 3 kilo ohm. So 10 minus VCE divided by the resistance, 3 kilo ohm. So 10 minus VCE is 0.2 divided by 3K, and this will be 3.26 milliampere. Now once we get IC sat, we can find out IB min. IB min is equal to IC sat divided by beta, which is 3.26 milliampere divided by 100, and that will give us 32.6 microampere. Now when we look at this IB, which is 21 microampere, and IB min, which is 32.6 microampere, we can see that IB min is greater than IB. This means our transistor is in active region, and that also means our assumption was wrong, but it was just an assumption, so it doesn't matter to us, right? Let's do the next problem. Here also there is a similar figure, but only the resistance has changed. Okay, again our assumption is that this transistor is in saturation region. Okay, so what will be IB? IB will be equal to 5 minus VB sat, which is 0.8 divided by the resistance, which is 50K. Now what will be the value of IB? This is 84 microampere. Now IC sat will be equal to 10 minus VC sat, which is 0.2 divided by the resistance 3K, right? And this is just as the previous value, that was 3.26 milliampere, and from this we can find out the value of IB min, which is equal to IC sat divided by beta, which is equal to 3.26 divided by 100, and that is 32.6 microampere. Now our IB is greater than IB minimum, right? If IB is greater than IB minimum, that means our assumption was right. The transistor is in saturation region. So this is right, because this IB min is less than IB. So we can do the next problem. Now this is the problem. Again, we have a circuit, we have to find the region of operation of the transistor. So from the previous cases, the only difference here is there is a resistance between emitter and ground. That means the potential of emitter is not now 0. Okay, so that makes the difference in this case. So here we have our VBE between these 2 points, and here we have our VCE. Okay, so we'll start with the assumption. Our assumption is that transistor is in the active region. Okay, so let's find out the values of IB IC and VCE and compare it with VCE SAT. So this is the input loop, loop 1, and this is the output loop, loop 2. So in loop 1, we can find out the current IB here. This is IB, and here there will be some voltage drop here. So there is a voltage drop in this resistance and a voltage drop in this resistance, and there are two voltages, 5 volt and VBE. So 5 minus VBE, that is 5 minus 0.7, must be equal to the voltage drops, right? That is IB into 50K plus, what is the current here? This current is IE. So IE into 2K. So 5 minus 0.7 is 4.3, that is equal to IB into 50K. And what is the relation between IE and IB? We know that IE is beta plus 1 IB for a transistor in the active region. This becomes beta plus 1 IB into 2K. That is IB into 50K plus beta is 100, so 101 into IB into 2K. 101 into IB into 2K. So now the answer becomes 4.3 is equal to 50K plus 202K into IB. Now IB is given by 4.3 divided by 50 plus 202 is 252K, and that will be 17.06 microampere. Now we can find out IC. IC is equal to beta IB, beta is 100, so 100 into 17.06 microampere, that is 1.706 milliampere. This is the value of IB. Now IE is given by beta plus 1 IB, and that is 101 into 17.06 microampere, and the value is 1.727 milliampere. Now we can look at the outer loop, the output loop. So in loop 2, there is 10 volt here, there is VCE here. So 10 minus VCE will be equal to the resistive drops, which is IC flows here, so IC into 3K plus IE flows here, so IE into 2K. So VCE is given by 10 minus IC into 3K plus IE into 2K, the brackets. And if you apply these values, you will get VCE as 1.416 volts. Now we know that VCE SAT for a silicon transistor is equal to 0.2, and the VCE we got is greater than VCE SAT. What does that mean? That means our assumption was right. This transistor is in the active region. Okay. So the region of operation is active region. Is it clear? The next question is this: in the circuit shown below, calculate the minimum value of beta required so that the silicon transistor operates in the saturation region. So in this question, IB is already given, as 0.1 milliampere. We know that IC is equal to beta times IB, right? Here we have our VCE. Now VCE can be written as 5 minus the drop in this resistance, that is 1 kilo ohm resistance, so IC into 1 k. Now that is 5 minus IC is beta IB, so beta IB into 1 k. Now we know that if the transistor is to be operated in the saturation region, the value of this VCE must be equal to VCE sat. So we can equate it here. This VCE is now 0.2 volt and this 0.2 must be equal to 5 minus beta into IB is 0.1 milliampere into 1 k. Km cancels. So that is 5 minus 0.1 beta. Now if we rearrange the equation, 0.1 beta is now equal to 5 minus 0.2, that is 4.8 volts, and beta will be equal to 48. So the minimum value of beta required is equal to 48. So we are stopping here. We will meet with more problems and more lectures in the next days. So until then, bye.